For more than a century, scientists have been seduced by the enigmatic allure of black holes. The idea, which started to gain significant attention around 1916, has evolved into one of the most compelling enigmas in modern astrophysics. These celestial curiosities occupy a fascinating intersection where gravity dominates and our understanding falls silent. A black hole, possibly between 2 and 4 million times the mass of our Sun, continues to be a cosmic riddle. Despite decades of intense research, our understanding has improved, increasing from having almost no knowledge to piecing together more details, with even more discoveries made recently. A breakthrough by M. Kaku has revealed startling insights about the interior of black holes, which may challenge our long-held beliefs and offer new perspectives on the nature of these celestial bodies. This new information opens the door to more in-depth investigations into what might have gone unnoticed until now. Come along with us as we expand into the fascinating world of black holes and uncover what's hidden within the universe's vast and inspiring expanse. But what are black holes exactly? As we delve into the latest findings by Kaku, it's essential to revisit the basic understanding of black holes. While most of us have at least a general sense of what a black hole is, some key elements remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At that time, the notion was purely theoretical. It wasn't until about 50 years later that evidence was discovered, confirming that black holes are real objects in space. In the 1960s, this revelation occurred during research on the star X1, a bright celestial body that emits X-rays. Observations showed that these X-rays were not just randomly moving, but were being drawn into a dense, invisible mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was monumental, as it proved that black holes were not figments of Einstein's imagination, but tangible, elusive entities that warranted further investigation. Following this groundbreaking discovery, scientists worldwide began a global quest to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may contain approximately 100 million black holes. However, because of the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that these massive entities number in the millions and are hidden within our galaxy, making it even more crucial to understand them. Let's break down the core concept of gravity. Black holes exert such immense gravitational forces that anything entering their domain is squeezed into a singularity, the point at which the rules of physics, as we know them, cease to function. In simpler terms, black holes are like gigantic vacuum cleaners pulling everything into them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become a singularity, their body torn apart by the intense gravitational forces before the point of total destruction. It's best to avoid getting too close to one. Though they are scattered across the universe, the nearest black hole, being nearly 500 light-years away, still raises legitimate concerns. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent aligning and taking pictures to create a single cohesive image. As more data was gathered, researchers discerned that black holes consist of 3 distinct layers. Contrary to the common misconception that they are just endless voids, the first of these layers is called the event horizon, which marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. The second layer, known as the photon sphere, is where light itself gets trapped, unable to escape due to the powerful forces of gravity at work. Finally, there is the singularity, where everything is compressed into a point of infinite density, a location where the very fabric of reality collapses, and all known laws of physics break down. What's even more intriguing is that each black hole is unique in its own right. While they generally adhere to the three-layer structure, the way they behave can vary significantly. Because of this, they are particularly challenging to study, as methods of conventional science do not apply to the study of black holes. Scientists have no choice but to investigate these anomalies through indirect means, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Sending a probe directly into a black hole is an exercise in futility, as anything that crosses the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on probes that would meet their end before providing any useful information. Consequently, researchers are left to study black holes in 2 dimensions, despite them being 3-dimensional singularities. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of physics as we know it. Theories about the origins of black holes suggest that they may form when massive stars collapse in on themselves. As a star consumes its fuel, it can no longer produce enough energy to counterbalance the inward pull of gravity, eventually causing its collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of black holes, NASA scientists turned their attention to the center of the universe, particularly the M87 galaxy. There, they observed a powerful whirlpool of hydrogen gas spinning at stupendous speeds of 1.2 million mph. The centrifugal force should have caused this gas to fly apart, but instead it remained intact, indicating the presence of an enormous object in the middle, most likely a black hole. This object is believed to weigh 3 billion times more than the mass of our Sun. One more important theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who utilized Einstein's equations to describe the behavior of rotating black holes. He argued that rather than collapsing into a point, as previously thought, a rotating black hole forms a structure known as a thin ring, called the ergosphere. This rotating disk of matter is key to understanding the breakdown of physical laws in the vicinity of black holes. Kerr's model also anticipated the existence of an Einstein-Rosen bridge, a theoretical wormhole that may provide an escape route through space-time, connecting distant regions of the universe or even parallel universes. To comprehend the concept of a wormhole, it's important to understand the concept of space-time, as described in Einstein's theory. Space-time is a fabric that has 4 dimensions and is twisted by objects with mass. This warping creates gravitational fields that influence the movement of other objects. Think of space-time as a piece of paper. If you fold the paper, you create a shortcut between 2 points. A wormhole's essence is a shortcut passage through space that has the potential to connect distant locations almost immediately. Despite the fact that wormholes are a theoretical concept and no direct evidence of them exists, they are a natural consequence of general relativity. However, wormholes are inherently unstable, which means they collapse quickly if created. Despite this, the idea of a wormhole as a potential gateway to different parts of the universe or even different points in time has piqued the interest of physicists for a long time. One particular kind of wormhole, known as the Kerr wormhole, has been a subject of fascination. Named after Roy Kerr, this theoretical wormhole could link 2 far-off points in space-time, possibly even connecting different time periods or universes. While the notion of utilizing wormholes for interstellar or time travel is exciting, there are significant challenges to overcome. For one, wormholes are predicted to be unstable, and the extreme radiation and forces surrounding them would make it nearly impossible to traverse them safely. Critics argue that Einstein's equations, while useful for understanding gravity, do not account for the quantum forces that govern radiation and subatomic particles. To truly understand black holes and wormholes, a new theory is needed, one that unifies gravity with quantum mechanics. This theory, often referred to as the theory of everything, is a quest that many physicists, including renowned scientists, continue to pursue. Researcher M. Yakubu has pursued for years one promising candidate for this theory, superstring theory, which suggests that subatomic particles are actually tiny, vibrating strings. The theory proposes that these strings create the universe's fabric, explaining not only gravity but also the phenomena surrounding black holes and wormholes. On the other hand, superstring theory also requires the existence of extra dimensions of spacetime that are so small they are impossible to detect. With current technology, despite the challenges, the pursuit of understanding black holes, wormholes, and the fabric of spacetime continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. Continuing, from where we left off, the pursuit of superstring theory and other theories that aim to unify the forces of nature is an ongoing challenge. However, it has the potential to open new insights into the very nature of reality itself. These theories propose that the universe is composed of more than the familiar three dimensions of space and one of time. In fact, they suggest that additional dimensions exist, but they are so minuscule and compact that we are unable to observe them directly with current technology. However, their existence could provide the key to understanding phenomena like black holes, wormholes, and the deepest mysteries of the cosmos. Superstring theory offers a fascinating picture of the universe, claiming that all forces and matter are manifestations of tiny strings that vibrate. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle. Just as a guitar string can produce different musical notes based on how it vibrates, the fundamental particles of nature might correspond to different patterns of vibration in superstrings. Proving this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the universe's structure. This could potentially provide answers to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together account for a vast majority of the universe's mass and energy, but remain largely mysterious. Yet, despite its elegance and promise, superstring theory remains unproven. One of the major hurdles in testing the theory is the fact that the extra dimensions it posits are so insignificant that they make predictions beyond our current observational capabilities to detect. To detect these dimensions, we would need instruments of unprecedented sensitivity and precision. Even then, the evidence might be indirect. This makes superstring theory a challenging subject to test through traditional scientific methods. Yet, its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also working on other approaches that might lead to breakthroughs in our understanding of black holes. For example, quantum gravity is another field of research that seeks to combine the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of large objects like planets, stars, and black holes. The hope is that by merging these two theories, scientists can gain a clearer understanding of how gravity works on the quantum level and, in turn, gain deeper insights into the nature of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is particularly important when studying black holes, because the extreme conditions near a black hole's event horizon, where gravity is extraordinarily intense, demand a theory that can account for both quantum effects and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most puzzling and extreme environments in the universe. The singularity represents a point where space and time become so warped that the usual laws of physics break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This has led to the development of ideas like loop quantum gravity and other quantum gravity models, which aim to resolve these contradictions and provide a more complete picture of black holes. As we continue to probe the mysteries of black holes, one thing is certain. The more we learn, the more we realize how much there is still to discover. Black holes are not just points of destruction, but are also places of incredible complexity and potential. Whether they are gateways to other dimensions, as some theories suggest, or whether they hold the key to understanding the deepest secrets of space and time, black holes remain an important field of study. As our methods and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be to refine our methods of observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can study the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamics of black hole mergers, and future experiments are likely to yield even more revelations. Another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes around the world, the EHT was capable of capturing a picture of the black hole's shadow, offering a glimpse into one of the universe's most mysterious phenomena.